In this group 2 video, I'm going to look at the reactions of the elements in the group. If we think about where these elements are in the periodic table, group 2 is part of the S block, and so all of the group 2 elements have an S2 electronic configuration. So what are they going to do when they react? They're going to lose those 2 electrons to obtain a full outer shell, and they would therefore become 2+ ions. Because they lose these 2 electrons, they are electron donors, and therefore when they react they act as reducing agents. And obviously we can show that by this simple half equation where we start with the metal and we turn it into the M2+ ion, and there's the 2 electrons there that it has donated. The metal itself has been oxidized because we're starting with a 0 oxidation number in the element form. Remember, all elements have an oxidation number of 0, and we're going to 2+, so that's an increase in oxidation number, 0 to 2+. Then obviously these 2 electrons will go on and be given to something else. The something else gains the electrons and therefore gets reduced. Hence the metals are acting as reducing agents. There's 2 reactions of the group 2 elements we're going to look at, and the first one is the reaction of the group 2 elements with oxygen. So you can see on the board I've just put a generic equation down where the capital M represents the metal, the group 2 metal, and you can see that the group 2 metal reacts with oxygen to form a group 2 metal oxide, and that has the general formula MO. And if you think about the charges within this ionic substance, we've got the 2+ ion from the metal, and oxide obviously forms a 2- ion. And so you just need one of each to cancel out those charges. So if we consider what's happening to the oxidation numbers now, you can see in red there, I've written a 0 above the metal in its element form. So oxidation number of any element is 0. And when group 2 elements are in compounds, which we've got here, it's got a +2 oxidation number. And so you can see the oxidation number has increased in the reaction, and that's obviously an oxidation process. And there you go, there's that half equation again there. So M turning into M2+, and there's those 2 electrons that this is giving away. So this is losing those 2 electrons and becoming the M2+ ion. And you can see there in orange we've got the change in oxidation number for the oxygen. So we're going from 0 to -2. That's obviously a reduction process. Oxidation numbers decreased. And there's the half equation for you. So if you remember, there's 2's here. So we've got this half equation here just for 1m. There are 2 in the equation. So effectively 2m's are going to turn into 2m2+'s and ultimately give away 4 electrons, 2 lots of 2 electrons. This 1O2 molecule here is picking up those 4 electrons. Each oxygen atom within the O2 molecule is gaining 2 electrons and becoming an oxide ion, and so we make 2 oxide ions as a result of that. Because we've had reduction and oxidation taking place in the same reaction, we would class this as a redox reaction. So because all of the group 2 elements do the same thing with oxygen, we can just apply this to any member of group 2. So if it was calcium, you just have a Ca there and a Ca there. If it was magnesium, Mg, and so on. If we move on to the reaction with water now, you can see again I've got a generic equation there where I've used M as the formula for the group 2 metal. So in general, group 2 metals react with water and they form an aqueous metal hydroxide with the general formula MOH twice. Remember, the hydroxide ion has a 1- charge, so you need 2 of these for every one of these M2+ ions. and we also get hydrogen gas. So in terms of observations, what would you see? Well, you would see the solid metal dissolving because we're getting this aqueous solution formed, and you'd also see fizzing due to the production of gas in the liquid. So we'll look at the oxidation and reduction processes now, and again we've got a zero oxidation number in the metal because it's in its element form at the start, and when it forms the hydroxide, it's a compound now. Group 2 compounds always have +2 oxidation numbers for the metal, and so this is our oxidation process. Oxidation numbers going from 0 to +2, and there's the half equation for what's happened there. So the metal has lost its 2 electrons and become the M2+ ion. The reduction process is a little bit more complicated to explain, so I'll do my best here. We've got 2 moles of water in the equation. Water contains 2 hydrogen atoms covalently bonded to the oxygen, and what happens is one of them is reduced and becomes a hydrogen atom. So if you have 2 of those in proximity, they will covalently bond and form an H2 molecule. So there's your reduction process there, going from +1 to 0 by the gain of that electron. The other hydrogen atom stays as +1. We've got a hydrogen atom within the hydroxide ion, still in the +1 oxidation state, and so that doesn't actually change. So the equation, the half equation that we would use to show that is this one here. So the 2 water molecules gain 2 electrons, and a hydrogen atom from each of these water molecules would each gain 1 of those electrons and ultimately become H2, and the other hydrogen atom remains in the +1 oxidation state. And we'll just finish this section with a reminder of those observations. So we would see the solid dissolving, we would see fizzing. Remember, the state symbols are a good place to look to get some observations out. And the other thing is, because the metal hydroxides are alkaline, then the pH of this solution formed would be greater than 7. We'll just finish by looking at the reactivity trend for both of these reactions. So, quick reminder, what do these metals do when they react? Well, there's the half equation. They give away 2 electrons. And so the easier it is for the metal to do that, then obviously the more reactive it's going to be. So if we think, well, how will this differ going down the group? Is it going to get easier to lose those electrons, or is it going to become more difficult to lose those electrons? So we'll just explain that by looking at magnesium and calcium. So magnesium has 12 protons in its nucleus, 12 electrons in the outer shells. So it's got that configuration, just simple configuration, 2, 8, 2. And calcium, it's got 20 electrons, so 20 protons in the nucleus, and it's got the configuration 2, 8, 8, 2. So you can see from these Bohr diagrams that the atomic radius for calcium is greater than the atomic radius for magnesium. So the attraction between the nucleus, the 20 protons in the nucleus, and the 2 electrons in the outer shell is going to be weaker for calcium because of that increased distance. And the other factor is the shielding factor. So remember, the protons, the attraction of the protons is shielded by any inner shells. So we've got 1, 2 inner shells between the nucleus and the outer shell in magnesium, whereas in calcium we've got 1, 2, 3 inner shells, and so there's going to be more shielding, greater distance from the greater atomic radius, and so calcium's electrons will be lost more easily. So calcium is more reactive than magnesium, and the trend continues down the group, and so the atoms become more and more reactive as a result.